All right, in this first part of section 3.5, we're going to look at what is called implicit differentiation. Now, we've seen lots of rules for differentiation. We have the product rule, we have the quotient rule, we have the chain rule. So all those are great rules, but implicit differentiation is when you have a function that cannot typically be written as y equals some function. So if you look at some of these, when you have powers on both the x and y, it would be very difficult to get y by itself, because when you take square roots, remember you have to add plus and minuses and things like that. So that's somewhat troublesome. So we have this method for doing what's called implicit differentiation, which is ways we can deal with things that are not really directly solved by y. So in general, it's pretty straightforward. What we're going to do is we're going to differentiate x as normal. So if you see just an x, we're going to differentiate it just like we always would. And we're going to differentiate anything with a y using the chain rule. Now, the way we're going to do this is anytime we differentiate something with a y, we're going to add a dy dx. Okay? So because we're not necessarily differentiating with respect to x, we're doing y, so we add this extra factor to account for that. So once you do a couple, they're actually not so bad. So we'll look at an example of how we would do this. So this first one says I want to differentiate 2x, or x squared plus y squared equals 9. So this is a circle with radius 3. So if I differentiate x squared, that's just simply 2x. Nothing kind of out of the ordinary there. When I differentiate y squared, if I pretend that's just a normal variable, that would be 2y. But we're trying to find dy dx. So what I'm going to do, because that's not x, I'm going to add a dy dx to that term. And then the derivative of 9 is just simply 0. Now the trick is we're trying to find dy dx. This is actually what we're trying to find. When we differentiate, remember we're finding y prime or dy dx. So we're really trying to find that dy dx that we now have in the problem. So how we account for that is we just simply solve for it, just using algebra. So I'll subtract 2x from both sides. So I get 2y times dy dx equals negative 2x. And then to get rid of this, since it's multiplied to the dy dx, I'm just going to divide both sides by 2y. So what that's going to give us is 2 dy dx is going to equal negative x over y. So when we do our differentiation of a different variable other than x, we add this dy dx, and then we're actually going to solve for it. In some problems, you can have multiple occurrences of the dy dx, but in general, we're just trying to get it by itself. All right, let's look at another one. So if you look at this next one, we have y squared plus 2y plus x squared equals 9. Again, this would be a really difficult one to get y by itself. But using the implicit differentiation, nothing too crazy at all. So the derivative of the y squared is just going to be 2y, but I'm going to add dy dx because it's not x. The derivative of 2y is just 2, again, times dy dx, plus 2x, and again, that's just an x, it's not a y, that's our normal variable, so I don't have to add anything, and that's going to equal 0. Now the trick in this one is we have to get the dy dx by itself. So what I'm going to do is I'm going to subtract 2x from both sides because I want to get the dy dx by itself, and so I'm going to get anything that doesn't have a dy dx on the other side. So we get 2y times dy dx plus 2 times dy dx equals negative 2x. And now the trick here is, since these both have a dy dx, I'm actually going to factor that out. So I'm going to take that out front, and then anything that's left is going to stay inside the parentheses. So that's going to be the 2y and the 2. Because if they have a common term in common, you can obviously take that out. And so now I'll just divide both sides by 2y plus 2. So my derivative, dy dx, is going to be equal to negative 2x over 2y plus 2. And since they're all even, what I can do is I could divide those all by 2 and just make it negative x over y plus 1. So that is my derivative. Okay, let's go ahead and look at just a general procedure to do this. So in general, we are going to take the derivative of both sides with respect to x, just term by term. Now you got to be somewhat careful though, because there are times, and we'll see this, sometimes you have to use the product rule, or the chain rule, or the quotient rule. Those are all come into play, so don't forget about those rules as we go through it. Then we're going to basically get anything with a dy dx on one side. We'll factor it out and solve it. So in general, these are pretty straightforward. Some of the derivatives can get a little hairy just because when you start doing products and quotients with this, the algebra just can get a little messy. So let's go ahead and look at this one. It says find dy dx. So the first thing I'm going to do is go ahead and take the derivative of each term. So the derivative of 2x squared is 4x. No need to add a dy dx for that. Minus 10y, because I'm bringing the 2 down, 1 less power. But I'm going to put the dy dx there, again, because it's not x, and we're trying to find dy dx. And that's going to equal 0. So now I'll go ahead and solve for dy dx. I'll subtract 4x. So we get negative 10y. Dy dx equal negative 4x. And then we'll simply divide out by negative 10y. So this is going to give me dy dx by itself, because these will cancel. On the other side, I have the two negatives that cancel. I have 4 over 10, which reduces to 2 over 5, x over y. So there's my derivative. Now, interesting thing about these derivatives, you'll notice that the derivatives have both x and y in them. So if I was going to find the slope of the tangent line, I'll both need the x and the y coordinate. If you recall, for our other derivatives are more, normal derivatives where you can solve for y, we just had to plug in the x because it was always y equals. So that is one difference. All right, let's go ahead and look at this one. Now this one's kind of a messy one. And the reason is, if you notice here, most of the terms are kind of the same. The one that's going to be somewhat problematic is this first term right here, x squared e to the y, because that is a product of two things. It's two things multiplied together. So remember, when you have two things multiplied together, you have to use the product rule, f prime g plus g prime f. So when we do this, we have to make sure we consider that this is the f and this is the g, or vice versa. So when I take the derivative of x squared, I'm going to get 2x times g, which is e to the y, plus g prime. Now the derivative of e to the y is e to the y, but since it's a y, it's dy dx, times f, which is x squared. And I'm going to go ahead and put the x squared out front here. Now I want to just stop here for a second, and if you notice, I have a dy dx on the second part, but not the first. Because in the first part, I took the derivative of x squared, not e to the y. But in the second part, I took the derivative of e to the y, not the x squared. So that's why I added it on the second part. And then I can continue. So now I have y. The derivative of y is just 1. But since it's a y, it has to have the dy dx. And that's going to equal 3x squared, because I'm just taking the derivative of x cubed. Now, if we look at this, how many dy dx's do we have? We have one here for this term and one here for this term. So to solve for that, I'm going to go ahead and subtract this 2x e to the y from both sides just to get it out of the way. So I'm going to end up with x squared e to the y dy dx plus 1 dy dx equals 3x squared minus 2x e to the y. So now if you notice here, these both have a dy dx. I'll go ahead and factor that out, and I'm left with x squared e to the y plus 1 equals 3x squared minus 2x e to the y. And then I'll just divide out. I'll divide out both sides by this x squared e to the y plus 1, and that will get me my final derivative. So you can see this one turned out to be really, really bad. So dy dx is going to equal 3x squared minus 2x e to the y all over x squared e to the y plus 1. All right, let's go and look at this one. Again, we have another kind of issue here because we have y squared cosecant x. Well, there's going to be another product rule. And then we have x sine y. Well, there's another product rule. So we've got a couple product rules here. So let's go ahead and just write that down from what we did on the previous page. Remember, it's f prime g plus g prime f. So if I take the derivative of f prime, so my f function is this, and this is my g function. So I'm going to get 2y dy dx times g, which is just cosecant of x, plus the derivative of g, which is the cosecant. Remember, the derivative of cosecant is negative cosecant cotangent times f. My f function is just simply y squared, and I do not need a dy dx for this one because I only differentiated the cosecant of x. And it will do the same thing for the x sine y. So I'll do this one. We have f and g. So f prime, the derivative of x, is just 1 times g, which is sine y. And again, no dy dx because I didn't take the derivative of something with a y. Plus the derivative of sine y. The derivative of sine is cosine, so it's cosine y dy dx times f, and the f is just x. I'll just put it out front. And it's going to equal, now it's 2 squared, but 2 squared is just a constant, so that's 0. So we have this ginormous mess that we have to kind of decipher. So this term has a dy dx, and this term has a dy dx, and the other two do not. So I'm going to add cosecant x, cotangent x, y squared, and I'm going to subtract sine y to the other side. So I'm going to do that to both sides. So what that's going to give me is 2y dy dx cosecant x plus x cosine y dy dx equals cosecant x cotangent x y squared minus sine y. So a lot of algebra to rearrange, nothing too crazy. I'm then going to factor out my dy dx. And so if I do that on the left side, I'm left with 2y cosecant x plus x cosine y equals this whole monster. And then I'll divide out by that stuff in the parentheses. So my final derivative is going to be cosecant x cotangent x y squared minus sine y all over 2y cosecant x plus x cosine y. So a really horrible derivative, but this would have been impossible to try to get y by itself. But with implicit differentiation, even these crazy kind of nightmarish functions can be done. All right, let's look at another example. It says, find the slope of the tangent line to a circle radius 4, centered at the origin at the point 2, 2 radical 3. So we have to kind of remember a little bit of our algebra. Any circle centered at the origin is always x squared plus y squared equals the radius squared. And so in this case, that would be 4 squared. So if I want to find the slope of the tangent line to this, so this is some circle that has a radius of 4. So this is 4, this is 4. So it looks something like this. So over 2, so we have this point, this is my point 2 comma 2 radical 3. I'm going to assume that's on the circle. So I'm looking for the tangent line at this point. So some kind of line that looks like this. So what I'll do is I'm going to find the derivative. I'll find dy dx. Now, nothing really crazy here, and this one's a pretty easy one. You get 2x plus 2y dy dx equals 0. And so we'll solve it for dy dx. So we'll get 2y dy dx, because I'm going to subtract that 2x term to the other side. And then I'm going to divide 2y to both sides. So dy dx is going to equal negative x over y. So now to find the tangent line, we need the derivative, because remember the slope of the tangent line is given by the derivative at that point. We mentioned earlier that you have to not only plug in x, but x and y for these implicitly defined functions. So we'll go ahead and plug in the 2 and the 2 radical 3. So my slope of my tangent line is going to be negative 2 over 2 radical 3, or negative 1 over radical 3. So now I want to go ahead and I have to solve this for my y-intercept. So if I want to do that, remember if I need to find the b, I can do y equals mx plus b. So y is 2 radical 3 equals m, which is negative 1 over radical 3, times x, which is 2. So we'll just make it negative 2 radical 3 plus b. So just to make life simple, we'll just make it be 2 radical 3 plus 2 over radical 3. Just adding that to the other side. So this is my nightmarish b. So my tangent line is going to be y equals negative 1 over radical 3x plus this horrible, horrible b. So if you graphed your original function, so if you graphed x squared plus y squared equals 16, or 4 squared, and you graphed y equals negative 1 over radical 3x plus that whole nightmare, you would see that that line matches up exactly where you see it. Now, the best thing we can see is the red line we drew does have a negative slope. Our tangent line has a negative slope, so we feel pretty good about that, that part at least. But check it graphically, make sure it checks out. You can also do higher order derivatives with implicit differentiation. Just takes a little more work. So this is a problem that we already did. And if I want to find the second derivative, I can certainly do that. Let's go ahead and remember what the first derivative was. So if I go back, remember dy dx for this problem was negative x over y plus 1. That was the first derivative. Now, if I want the second derivative, what I'm going to do is I'm going to take the derivative of both sides. Admittedly, these do get pretty nasty, because on the right side, you'll notice I have a quotient, f and g, so I have to use the quotient rule, f prime g plus g prime f over g squared. So let's go ahead and see how this works. So if I take the derivative of the left side, the dy dx, I will get the second derivative, dy dx squared. So my second derivative is going to be the quotient rule of this. So this says take the derivative of the top. So the derivative of the top is negative x, so that's just negative 1 times g, which is y plus 1. And I don't have to add any dy dx in this case because I differentiated an x. Plus g prime. So now the derivative of the bottom, the derivative of y plus 1, is just 1. But I'm going to need a dy dx because I differentiated a y and not an x. Times f, which is times negative x, all over g squared, which is y plus 1 squared. So I have the derivative, second derivative, but the problem is, if you notice here, I have this derivative here. So here's the trick with the second derivative. Well, we know this is the first derivative, and this has the first derivative in it. So we're going to plug this in here. And we are not going to simplify, as you will see. So we get d squared y over dx squared. And that's going to be negative y minus 1. I'm just distributing that negative 1. Minus x, I'm going to move that in front, times the first derivative. So that first derivative actually is going to go in my problem. All over y plus 1 squared. We're going to keep it like this. This is fine. So you can do a second derivative, but in general, when you do the second derivative as part of that problem, you will inevitably end up with a first derivative, which you'll then plug in because you already know the first derivative. All right, so this is the first part of our section 3.5 on implicit differentiation. We'll use implicit differentiation in the second part of it as well, but not as a necessity, but as kind of a shortcut to do some of our earlier derivatives that we saw. Obviously, if you have any questions about this, please let me know.